Okay, welcome everyone. So we have first presenter is George Paconis. He is a second year master student in ETH, and he has interest in working on data-driven microarchitectures, machine learning, how to apply machine learning in computer architecture to design high performance and energy efficient processors. So he is going to present Constable, improving performance and power efficiency by safely eliminating load instruction execution. Hope you would be liking the presentation and engage him as much as possible. Okay, George.
Okay, perfect. Thank you. No. No, I think the slide a little bit low. Yeah.
No, I'm not sure where exactly it's coming from. It's non-hoverable. Yes.
Okay. Great. Perfect. Can you hear me? Yeah. Hello, everyone. My name is George, and I'll be presenting Constable, a technique for improving performance and power efficiency by safely eliminating load instruction execution. This paper was presented in ISCA 2024. One of the first authors is Raul as well, and this is a collaboration between ETH Zurich and Intel. Okay, this is not working. It's not working. Should I use that? No. Okay. Okay. Perfect. Perfect. Okay. This will be my presentation outline. First, we're going to see the motivation behind this work, then characterization of different workloads. We're going to move on to the Constable, the key insight, and the design aspects of it. And we'll conclude with the evaluation results and strengths and weaknesses of that paper. Let's start with the motivation. We always strive for higher performance in our applications and in our systems. One way to achieve high performance in the processors are, of course, by extracting the instruction level parallelism. But there are some limitations there are some issues that limit us in order to extract as much instruction level parallelism as possible. One of those reasons, of course, are data dependencies that are due to the data flow between the instructions. Here I have two instructions where the second one is depending on the first, and it cannot be perfectly pipelined. Another reason are the resource dependencies that happen when two instructions contend for the same hardware resource that are limited inside our systems. Those can be execution units, load ports, or other parts of the system. And besides the previous two, there are control flow dependencies that are dealt with using branch predictors, which is outside the scope of this work. One significant the instruction that causes significant problems is the load instruction, because for many reasons, but the main ones are that it consists of two distinct operations. First is the address calculation that is complete during the execute stage, and it requires a reservation entry and an address generation unit. After that, in the memory stage, we need to fetch the data from the memory hierarchy, and that requires a load port into the first level cache. Multiple approaches have been developed, multiple techniques, in order to try to mitigate the load data dependence. One of them is called load value predictor that try to speculatively execute the load dependent instructions using a predicted value. Another one is called memory naming that try to learn the dependence between a store and a load instruction pair and speculatively forwards the data straight from the output of the source to the dependence of that load. However, these two techniques try to mitigate the load data dependency via address speculation, requiring the need to execute the instruction to verify the correctness of the speculation. This leads to those instructions failing to mitigate the resource dependence that might occur in our system. Here we have the executive summary. This is the problem that I previously described. The instruction level parallelism is essential for high performance processors, but it is limited by low data dependence and low resource dependence. As the motivation for this work, the existing load elimination techniques try to break the load data dependence, but they require to execute the instruction to verify the speculation, consuming the limited hardware resources. The key idea behind Constable is to safely eliminate the load instruction, both aspects of it, both the address calculation and the data fetch, without the need for speculation. The key insight that enables this idea is that two dynamic instances of a load instruction fetch the same value from the same memory location when none of the source registers of the load instructions is altered between the two instances, and no store or snoop request has arrived to the memory address that is calculated from the first instance. This paper proposes a Constable, a completely hardware architectural technique that can dynamically identify the likely stable load instructions that match these two previous conditions, track the modification to the source architectural registers of the load instruction and its memory location to ensure that these two conditions are met, and eliminates the instruction execution using the last fetch value of the load instruction. The Constable is evaluated in a variety of workloads, and this evaluation has revealed that we can achieve over 5% of performance increase over a baseline system. When it is combined orthogonally with a state-of-the-art load value predictor IFS, the performance increase 20.5%, and besides the raw performance, we also expect improvement in the power domain, where Constable reduces the reservation station allocation and cache access by 8.8 and 26% respectively. Moving into the characterization of the real workloads, as we saw in the executive summary, Constable targets the global stable loads. Loads we call global stable loads the loads that fetch the same value from the same load address across the entire workload trace. With the characterization of various and distinct workloads, we see that over 1/3 of all dynamic loads in a system are global stable. From this characterization, we can conclude that global stable load instructions appear in different addressing mode and inter-occurrence distance, and our proposed technique, Constable in that case, need to accommodate for all these differences in the load distance, in the load instructions. Besides the global stable loads, the authors of this paper proposed another metric, the load utilized cycles, that are cycles where at least one of the port is utilized. Out of the total cycles of the system, we can see again that around 1/3 of all the total cycles are load utilized. From the load utilized cycles, 23% of them, in 23% of the cases, a non-global stable load is waiting for a global stable load on the same port to be executed. This leads to the conclusion that in the absence of the global stable loads, the non-global stable ones can be executed faster, leading to significant performance improvement. Of course, we don't want to do any other stuff. We want to offload it to the compiler side, but unfortunately, we saw that in the real workloads, the compiler often fails to eliminate 34.2% of the global stable loads. Why is this the case? This is the case because the compiler needs to be certain about an instruction to remove it, and this certainty can only be achieved during the runtime, which the compiler, of course, does not have access to. One example that the authors of the paper presented is this one, where a pointer variable is initialized only once during the runtime, and it acts as a runtime constant. This load instruction, for this load instruction, the compiler fails to eliminate it. However, it's still a global stable, and it does not need to fetch the data multiple times. The authors of the paper tried to evaluate the performance headroom of Constable, having an ideal case where all the global stable load instructions are calculated and identified online. Here in the x-axis we have the different workloads, and on the y-axis we have the speed up over the baseline. The different techniques that we compare with is, of course, the ideal Constable that breaks the data dependence and the resource dependence, both aspects of it, both the address computation and the data fetch. The ideal stable load value predictor, where we again break the data dependence, but the load is executed. And another version of it, where the data fetch elimination, the data fetch is eliminated, and only the address computation is executed. The final comparison in that table is with a system that has twice the number of load execution units. From this figure, we can conclude that the ideal Constable achieves a 9.1 performance improvement over the baseline. Eliminating both parts of the load execution instruction results in almost 5% increase in performance. This is the comparison between Constable and the ideal load value predictor. And finally, the ideal Constable still outperforms the machine with which has the doubling the load execution units. With, of course, that comes with significant lower area and power requirements. Moving on to the Constable key insight, the whole Constable idea can be distilled into this sentence that a dynamic instance I2 of a static load instruction I is bound to fetch the same value from the same memory location as the previous dynamic instance I1 of the same static load instruction. This happens when two of the following conditions are satisfied. The first condition is that none of the source architectural registers of I has been written between the two occurrences. This has a consequence that I2 would calculate the same address as I1, and thus allowing us to safely eliminate the address computation of I2. For the second condition is that no store or snoop request has arrived in the memory address of I1 between the occurrences of I1 and I2. This has a consequence that I2 would fetch the same value from the memory location, from the same memory location as I1, and thus the data fetch operation can be safely eliminated. For the overview of the system, we saw also in the executive summary that Constable targets the elimination of likely stable loads. These are loads that fetch the same value from the same address over the workload execution. For the loads that are classified as likely stable, Constable tracks the modification to the source registers and memory location in order to verify that the conditions are met, and then proceeds to eliminate the execution of that load. Constable, by breaking the data dependence, providing the previous calculated address and fetch value to all the load dependent instructions until one of these two conditions is broken. Moving on to the design, this is an overview of Constable. Constable consists of three core components: the stable load detector, the register monitor table, and the address monitor table. For the stable load detector, this is a table that is indexed by using the program counter. It stores the last calculated address and last fetch value of the load instruction and decides if the execution of that load instruction can be eliminated if it surpasses a specific threshold. And then it provides the load dependent instruction with the required value. Moving on, we have the register monitor table, which enforces the first condition. This is a table that is indexed using the architectural registers, and it monitors the modification to them. in each entry, it stores the list of loads that are eliminated and have as a source that specific architectural register. In the case of a new instruction having as a destination register that index, the RMT resets the eliminate flag for all the loads in that entry. Similarly, we have the address monitor table, which enforces the second condition. This is a table that is indexed using the physical address, and it monitors the modification to the physical memory. It again stores the list of loads that are eliminated and have calculated that this index is the specific address. In every store or snoop request to that address value, the AMT again resets the eliminate flag for all the loads in that entry. However, besides only needing to identify the likely stable loads that is done that I explained in the previous slides, we need to also break the data dependency and supply the load value address to all the load dependent instructions. For this, the authors of this paper used a well-known technique called mover elimination that is also used in other papers. A Constable stores a value into a small register file called xprf, and then it converts the load instruction that is decided to be eliminated into a fake move one. And then this fake move load instruction loads the value from that register file. This fake move instruction is completed during the rename stage of the pipeline by passing the remaining pipeline stages and supplying all the load dependent instruction with the appropriate value. I also mentioned something about the confidence threshold. This confidence threshold is a mechanism that limits the candidate loads to track inside the Constable structures, mainly the AMT and SLD. Of course, we cannot track every access to all the memory addresses, and we need a way to limit the loads that we care about. This confidence threshold, Constable, during the retirement of a load instruction, Constable checks the previous instance of that instruction, and if the load address and value match, the confidence level is appended by 1. If they don't match, the confidence level is then halved. When the confidence level is greater than the threshold, the load is classified as a likely stable and can be eliminated in the next occurrence. The paper has also many more implementation details in order to resolve every single one of those problems. I'm not going to go through all of them, but I have backup slides if you want to discuss any particular one of them. But they provide the extensive reasoning behind and solutions behind all these problems. The Constable has this storage overhead, which is 12.4 kilobytes, excuse me. And as we can see in the evaluation state, this is significantly less than all of the other comparable techniques that try to eliminate the load data execution. Speaking of the evaluation, on the right, there is a table that is the simulation parameters, and the most important aspect of that paper is the comparison of Constable. These are the early load address resolution, which is a technique that safely eliminates the non-speculatively address, non-speculatively, the computation of the need to compute the address that correspond to stack loads. However, important information is that this still needs to fetch data from the memory. Moving on, there is a register file prefetching, which predicts the address of a load to prefetch its data in the register file, and IFS, the state-of-the-art load value predictor that tries to predict the next value of a load instruction. Here in this graph, we have in the x-axis the different workloads that Constable is evaluated upon, and on the y-axis the speed up over the baseline. These workloads are sorted by the performance of IFS over the baseline in them. We can see that out of 60 out of 90 workloads, Constable outperform Eves by close to 5%, while in the remaining 30, Eves outperform Constable by 9.2% on average. From that figure, we can conclude that Constable provide a significantly performance benefits over the baseline, and combining both Eves and Constable results in a better performance over each individual technique alone. The authors of that paper also would like to depict how close we are to the ideal case with the actual implementation of Constable, as we can see in that graph, where in the x-axis we again have the workloads, and in the y-axis the speedup. We can see that Eves plus ideal plus Constable is really close in the terms of speedup to Eves plus the ideal Constable implementation. Besides that, not only in the performance aspect, in the overall speedup, but Eves plus Constable is also comparable to the load coverage of Eves plus ideal Constable, with the first approach having 35.5% of all the loads being detected and eliminated, while in the ideal case we have 41.6%. Another figure that tries to explain the and to break down how Constable affects the loads and which loads are eliminated is that figure. Here we're going to start with the black bars that are the global stable loads that are eliminated using Constable. Constable can successfully eliminate 56.4% of all the global stable loads. Moving on, in the gray bars, we can see that some loads are global stable, but Constable fails to eliminate them. These are 43.6%, and the reason behind Constable failing to eliminate them can be explained in the following points. The first one and the most significant one is that the architectural register changes between the two occurrences in 23% of the cases of the global stable loads. And another one is the silent load, where the last store before the second instance restores the original value. This can be classified as a global stable load, but Constable fails to identify this as such in 14% of the case. And some other reasons that are attributed to confidence learning and limited hardware budget in 6.2% of the cases. Besides that, however, we can see that Constable can eliminate some non-global stable loads as well. And this is on average 13.5% of non-global stable loads that are eliminated by Constable during runtime. This is because these loads are not stable for the entire workload, and thus not classified as global stable, but are stable for a significant part of it and meeting the threshold, the confidence threshold that is set by Constable. Besides the performance, we also the authors of the paper present also the resource utilization and the improvement that Constable provides. We can see in this table that Constable reduces the reservation station allocation by 8.8% on average. While Constable also reduces the need to go to L1 cache by an impressive 26% on average. We can conclude from this to figure that Constable significantly reduce the resource utilization and subsequently the resource dependence that the loads experience. The limiting the resource utilization, of course, entails some power improvements. As we can see in that figure, Constable reduces the overall core power consumption by 3.4%, while Eves only reduces by 0.2 because Eves needs to execute the load instruction in order to verify that our speculation was correct. And then, for the conclusion, we introduced Constable, a technique to safely eliminate the execution of a load instruction while breaking the load data dependence. Constable provides a significant performance benefit and dynamic power reduction, on average 5.1%, and when combined with Eves value predictor, the performance gain can reach over 8.5%. Okay. Before I move on, do you have any questions about the paper before I move on to the strengths and weaknesses? Yeah.
Since some of the non-global stable loads are eliminated, is the functional correctness impacted?
No, out of all the workload traces, the functional correct the execution is completed without any failures, so this does not affect it at all.
So in slide 24, you mentioned that in 23% of the load utilized cycles, a non-global stable load is waiting for global stable load. And if we can eliminate them, we get at most 23% performance improvement, right? Why is it able to go beyond if we have 2x more load ports?
Sorry, can you repeat it? I didn't quite understand it. Because
so in slide 24.
Yes, 24.
We said 23% of the load utilized cycles, non-global. So non-global stable load is waiting, right? So if we eliminate them, we get 23% more, ideally, performance improvement. But in slide 29, it's able to surpass 2x load execution width.
Yes, because sorry, I'm keep pressing the wrong button. Yeah, because the load doubling the load execution units can also have other issues. Of course, we cannot, maybe it is not efficient the amount of load ports in our workloads, but as well, it can also have a contention with the other part, not only the fetch, the data fetch, but also in the address computation part of the load. Any other questions? No? Can I move on? Yeah. Okay, for the strengths of and the weakness of the paper, of course, we're going to start with the strengths. This paper presented a really clear idea that is simple conceptually and easy to understand. It identifies the ideal performance headroom of Constable and explored the distance of the actual implemented system to the one using the offline calculation. It identified the sufficient conditions for safe elimination of the load instruction. And this is a purely microarchitectural technique that is integrated directly in the hardware, and it does not require any additional support from the operating system or the software. Yeah. The paper presented all the niches of the implementation. Some of them I skipped during the presentation, but they are present in the paper, and the incorporation into the existing pipeline, considering all the aspects with sufficient reasoning behind each and single one of them. The paper presents an extensive evaluation of the Constable technique in various and different workloads for both performance and power consumption measurements. And it provides a detailed explanation of Constable ability to eliminate stable loads, as we saw in a figure where Constable can safely eliminate global stable loads. Some of them it fails, and it eliminates some non-global stable ones. For the weaknesses, the most important weakness that I was able to find in the paper is a security vulnerability. Because we eliminate a load instruction, we alter the timing of its execution and thus we gain performance. This is not a problem when we have a normal issues user, in that case, this police officer, but in some cases where we have a malicious entity that tries to gather data from our execution, this could also be a problem. These type of attacks are known as instruction timing attacks, where they are able to extract information by observing the difference in time to execute instruction. Of course, this is not only a problem in Constable; this is a problem general in processors, but Constable would make it more severe. Some attacks that I have here are called. The first one is called flash reload, which try to observe the difference between accessing data from cache and the main memory. This, of course, can be expanded to be able to differentiate between eliminated and not eliminated stores, loads. Actually. Some other attacks that I also included are zombie load, microarchitectural data sampling, meltdown inspector, and RSA timing attacks in order to be able to gather information from the system. Another weakness that I thought the paper has is that the condition assumption is sufficient, but is not necessary. In some cases, it's too restrictive. Author mentioned that issue, that Constable fails to eliminate stable loads due to silent stores that restore the original value before the second instance of the load. This paper acknowledges that, and however, it leaves significant performance on the table. Around 14% of all global stable loads are not eliminated because of that reason. Another weakness of that paper is that the authors didn't fully explain the decision about the confidence threshold, neither its value nor the updated policy. It seems a little bit arbitrary decision to make. They didn't thoroughly explain it. They used 5 bits for the confidence level, and they set the threshold number to 30. It would be nice in that paper if there was a diagram that depicts the impact of a different threshold values to the size of Constable tables and the performance impact that would entail. Another issue, maybe more on the more technical side, is that appending structures to the pipeline stages may negatively affect the critical path. Constable, with its inception, targets high-performance CPU systems with over 4 GHz of performance. Constable structures maybe are not that big in storage requirements. However, they could cause significant delays in latency and issues with the critical path in the processor itself. It's not clear if the author considered this when evaluating their technique, neither on the performance side nor on the power domain. Okay, these are the weaknesses. Before I move to the discussion points, do you have any questions about those?
So Constable sits per core, correct?
Excuse me?
Constable is per core, right?
Yes.
So what about shared data modification? If other core is modifying shared data, how does Constable take care of this?
This is the coherence mechanism that is mentioned in the paper. I have a backup slide about the coherence. Yeah, this is how to maintain coherence in the system. Yeah, the font is not that great, but yeah. Okay, most of the modern CPU implementation have directory cache coherence protocol, and the way that this cache coherence protocol and how this is a problem with Constable is that the only cores that the cache line is present will receive a snoop invalidation request, and here the address monitor table would decide to reset the eliminate flag. However, during the clean eviction case, which is a problem that is presented in the paper, the data may be not in the cache. However, it can still reside inside the stable load detector table. In order to resolve, that of course could lead to a wrongful execution, because someone else wrote in that cache line, but the stable load detector is not able to reset and load the new value. The way that Constable resolves this issue is to pin the core in the directory entry and remove the pin when the Snoop request is delivered. That way, it can ensure that the Snoop request would reach this core and the Constable structure in order for the address monitor table to detect it and reset the canon emulate flag. Okay. Yeah, not my spoilers. Yeah. Okay. Some other question about the weaknesses of the paper? Let's move on. Of course, we have to resolve the security concerns that are increased because of the presence of Constable, as Constable may introduce new instruction timing attack possibilities. Do you have any idea how to mitigate or resolve those effects? Mm-hmm.
I don't know if this would be possible, but maybe we could insert like some sort of dummy lows for those that we replaced.
Yes, that will be possible. That is the second, similar to the second approach, where we inject random delays to the program execution that to scrub the timing information so the malicious user is not able to detect or to gather significant information to be able to identify which data are we loading. Another one is to use constant time algorithms. The timing attacks mostly target cryptographic operation. We can ensure using those algorithms that cryptographic operation always take the same amount of time regardless of the input, limiting the probability of the system experiencing an instruction timing attack. Some other idea?
I have a question about the constant time algorithms.
Mm-hmm.
My understanding was that the algorithms used already are constant time anyways, but when the hardware doesn't operate the way the programmer like expected it to be, like a constant time algorithm probably wouldn't change that, right?
I guess I'm not that familiar with the way that this is done, but I guess there is a way to enforce the CPU to execute all the instructions in a specific time. I have some idea about, let's say, the real-time operating systems, where they ensure every thread, every part of the operation is executed during a specific amount of time because of criticality and others. And this can also be employed inside the hardware to ensure that constant time would be retained. Some other, of course, the most easy approach is to enable the ISA support to allow for the programmer to pin the global stable loads as entries inside the SLD. This, of course, could lead to more performance if the programmer is smart enough to place these global stable loads. But can you find any problems with that approach?
Like more complexity for the programmers?
Yes, besides that, yeah, of course. But there is also another issue of privacy because the SLD table is shared across both the hardware as well as the software threads inside a single core. This isolation is achieved when every time we have a context switch inside the CPU, all the tables, all the Constable structures are flashed. However, we still have to ensure that if we pin an entry inside the SLD table, what would happen in that case if it would be flashed again and then reloaded, or other issues as well, in order to ensure that the privacy between the different threads. Another one about the conditions. The conditions are sometimes too restrictive to detect all the global stable loads. Can you think of any other conditions that would allow for more flexibility? I remember the silent stores.
Well, I think I was just looking at another paper which talks about eliminating silent stores. So if you eliminate silent stores, then maybe
Yes,
you can.
Yes, you can significantly improve the performance. However, here, of course, this is correct, but here I have some change in the conditions of Constable. Instead of resetting the eliminate flag in every store, we could compare the value of that store with the previous fetch value of the load instruction. So if we have a store operation that just restores the same value as the first instance of the load, the second instance would not be, the store would not lower the threshold level, would not have the threshold level. If we have multiple stores, we could have a buffer in the presence of multiple stores to always check for the last one before the next occurrence of the load. And that way we can identify if there's a silent store, and if it is, then continue to eliminating the second instance of that load.
Why do you need a buffer to store multiple stores if you only want the last one?
Yeah, that's a good question. I thought, yeah, now that you can override it. You can override it. But my idea is that you also have the store buffer. You can check it with that. But yeah, you're right. You only need the last one. Yeah, check for the last one.
Does the paper also talk about why it doesn't want to detect silent stores?
Yes, in the paper they mention it. The way that this happens and the way that Constable fails to detect these global stable loads is that in every store request that happens in the same memory as the load, it just halves the threshold, the confidence threshold of Constable inside the SLD, and that would lead, of course, to loss in the can eliminate flag, and we're not eliminating the second instance. And another one. I think I found it somewhere online. It's called the load bypassing or forwarding. In every write of the source architectural register or a store or Snoop request, Constable halves the confidence level of that instruction. In the case of a store or Snoop request, do we always have to invalidate it? Maybe if it's a random store somewhere, it's not often happening. Here, the one idea that I got is to have a second store tolerant threshold where if you were above this threshold, Constable can tolerate changes in the load value before it invalidates. If they forwards the data, if a store occurs, or a Snoop request, directly to inside the SLD entry in case we are above this threshold. Yes, this I thought this idea because SLD can also act as a form of cache in an abstract way, not necessarily, but yeah. Any other ideas? Okay, then that's it for me. Thank you very much. Yeah.